It also means we lose all the announcements that you just saw right here on this page, but we'll use this little trick. Screenshot always helps out. Well, I think we can start. Welcome back, everyone. For today's class, our goal is to finish off chapter 11 and start our segue into the more abstract section on sampling distributions. Using ideas with the central limit theorem, we're going to be able to take our normal distribution way out of where you think it would work and have it become very effective in surprising situations. Even when the data isn't necessarily quantitative, you can sometimes use the normal distribution for statistical analysis. It's really very surprising, and the central limit theorem is what does it for us. We mentioned before in class, this is a pretty abstract chapter. We'll take our time with it. We'll do kind of a preview with it today just to get kind of the setting set up for us. But if you do pre-read it, that'll help you out quite a lot when we come back next week and start working through there. I did write this out though. You might not want to read the entire thing. If you did the section on working on p-hat, that's where we're adapting the central limit theorem for categorical data with two outcomes. But we're only going to really study that section once we get into the relevant chapters for the categorical data. So we'll leave this thing hanging there and come back to it when we need it. Well, for the other announcements, let me scroll back to here. Our assignment number 2 is going to be due next Monday, involving just information from chapter 2. And this is pretty much our pattern for attack on all the assignments. The moment we finish a chapter, we'll have our assignment due 1 week after. And these are usually just my guess. I'm guessing that we're going to probably finish chapter 11 today. But if we take a lot of questions, if there's interesting discussions, and we just need more time, we'll take that extra time and adjust the due date down here. So the schedule for this class is pretty wide open in that sense. Only thing that's firm are the exam dates. Well, any questions or comments at all, folks, before we get started with today's work? Oh, I forgot about Zoom. Sorry about that, folks. All right, we've got the participants windows back. How about for folks in Zoom? Any questions or comments at the moment? Okay, looks like we're about ready to get started. We're going to go back to chapter 11 on example 3. But before we do that, let's kind of also refresh ourselves on what we've been doing. This is essentially the model that we're working with. It's referred to as a continuous probability model, where probabilities are areas under a certain curve called the density curve. This blue curve right here has a pretty complicated function for it, with an exponential function to go along with it. But the most important thing is, if you're asked a question like this, what is the probability that x is less than 50? What you would do is find the value 50. Here on the horizontal axis, we'll accumulate the area going to the left, matching the direction of the inequality. And we can find through technology that this particular area is 0.1870. And so we have a 0.1870% chance, or a probability of 0.1870, that the event here will occur. What was it? X is the length of a randomly selected fish. So it's saying there's about a 20% chance, if we round roughly, of finding a fish less than 50 millimeters, I believe, for that population. So that's our idea of probability so far. Then what we did next was we took a look at this picture, not because we're going to directly use this rule. It's almost silly to use that rule when we have really powerful calculators like RStudio or even other things. So we're not going to worry as much about using this rule, but it's still an interesting picture because it tells you the role that the standard deviation plays in controlling this curve. Standard deviation was meant to tell us how spread out our data is. And the larger this is, the standard deviation, the further the curve is going to push out to the right and the left simultaneously. You'll have 68% of observations within one standard deviation, the mean, and 95% within 2, and so on down the line. So that tells us what exactly the standard deviation is doing. Provided our data is mound-shaped, at least roughly symmetric, this becomes a wonderful model. Next, we took a look at when might the model actually work well. Not for uniform data, it's not mound-shaped. It's symmetric, but that's not good enough for us. This is a little bit better. It's got the mound shape we like. It has the symmetry. But once you get to these things, this is not good at all. For data that's highly skewed, we cannot directly model these data using a normal distribution. But there is something related to this that we might possibly model if the sample size was large enough. That's getting into the central limit theorem. And that's why the normal distribution is weird. Not because it works all the time, like say for these data. It fails in a lot of situations. And it's also, in all honesty, a mathematical fiction. I mean, it's that function. There's no reason why that specific function should model, say, like the height of people in the 5th grade or something like that, where people say it should be distributed normally. This is just our best attempt to put a curve to data, nothing else. But it becomes less of a mathematical fiction and more something that's actually honestly important once we start doing statistical methods. It becomes a fact about reality, which is kind of strange in a certain sense. But that's the central limit theorem we'll be getting into. And because of the central limit theorem, we really need to work with the normal distribution. And that's why we're doing a couple of these kind of problems, just to get our head around the normal curve as we go to the next stage. So in this particular problem, X was the random variable. It represents a randomly selected person from this particular study. They're measuring reaction time to brake lights. So X is reaction time to a brake symbol for a randomly selected driver from this study. We wrote out that the mean in the study was 1.25 seconds. And we can't use a parameter here because we're regarding the study as a population now. The parameter sigma at 0.46 seconds was stated. And so we said the probability distribution of X should be modeled this way. Tilde says is distributed as N for normally distributed, with that as the mean and that as the standard deviation. Our first probability computation looked like this. We had to calculate the probability that X, reaction time to a brake light, is between 1.75 seconds. The graph would look like this. It's always a good idea to put the center just to make sure everything's kind of in the right spot. And probabilities are areas like we mentioned, so we needed to find this area. In RStudio, that's the syntax that made it all happen, and it outputted 0.5681. In fact, RStudio saved our work that we did from the other day. Here's what it looks like. Let's just run it again. We get 0.5681 after rounding to 4 decimal places. So typically when you're doing this in RStudio, it's a good idea to store your parameter values to start. You would probably really just be looking right here in your description when you bring them in. Then I'm just going to pretty much format my work right here like this. Let's move next to part B. And I'll put down the script once we finish out the whole problem. But before we move to the next part, any questions or comments, folks, about any of the recap or part B down here? Oh, let me bring the window back. It's always a little tricky working at these windows, trying to find the right spot to put everything in, but we'll get better as we practice with this. Well, let's try this all out again. Part C now asks us, calculate the probability that X is greater than 2. And whenever you see that X, try to force yourself to read out in your mind, even though it's going to take a while to read these out. Read that as the brake light reaction time for a randomly selected individual greater than 2 seconds. That's the probability we want. If you force yourself to read that out every time, you'll help out with these instructions. And in a really certain sense, when you give a practical interpretation to a probability, this is kind of the real deal for the course. This is statistical methods of communicating your results once you see these kind of responses right here. So these instructions are going to become really, really common. I'll try to say it in the same way, and we'll say what we mean when we mention context. You just have to say something about what the study is actually talking about, brake signals and units and such. So here's our next try at this. If you like, you could just type out the syntax to this. Give me one number, like the 0.5681, and that could be your whole answer, other than the practical interpretation we provide. But when you're learning this, if you ever want to look back at your homework that once it's graded and returned to help out with other things, it might not be a bad idea to add just a little bit more detail. So what I'm putting here is my best attempt at a freehand sketch for the normal curve. Not too shabby this time. We know the center is at 1.25, so that's the mean mu for the population. We're asked to do this, probability X bigger than 2, or find this probability, which is in turn finding an area. I'll leave it blank here for the moment. And now we just need to put 2 seconds somewhere on the curve. The standard deviation is about 0.5. So here's where the inflection is. This would be about 0.75. I'd guess 2 is around here. We're not trying to put it in perfectly, but just get a good ballpark location for where it should be. Now that we have that, I'll just shade a little bit to the right. There we go. Here's 2. And to get this value right here, the syntax would be, I'll write it here in pen, and we'll copy it down from actual RStudio at the end of the problem. But this area, you can find it by doing pnorm. You have to get the value on the horizontal axis, 2, that where the area starts. Then put in your value for mu, sigma. I stored them as mu for mu, sig for sigma in RStudio, so I'll write them out this way. But now that we're doing area to the right, there's one other option we have to control. By default, the pnorm function is going to accumulate area going to the left, but we want greater than area to the right. So what we do is we say lower dot tail equals false. So control that option, and you're now doing the upper tail of this area right here. So let's implement that and see if it actually works. So for part P, we're going to put in pnorm 2 from right here in the question. Mu and sigma, let me try to get that off of there. Mu and sigma are pretty much always going to be the next 2 inputs, no matter what, since those are the stated parameter values. But this one is a little bit special. We have to control the lower tail, lower dot tail, set to false. If you have that set in, then we should be getting a probability that's small as opposed to something close to around 0.9-ish. Okay, let's give this a try. Probability comes out as a 0.0515. So let's write that in. Probably should use the black pen, make it more official. 0.0515. And we did it, folks. That looks about right. If I forgot the lower tail equals false on this, here's how it would have came out. We have a close to a 95% chance that x is bigger than 2 by this syntax right here. And even if you didn't draw this, I'm just drawing it so it's part of the notes. Even if this wasn't on your paper, just try to visualize it on your mental chalkboard and you'll know, hey, that was supposed to be small. 2 is far from the mean, far to the right. There's no way that's right. The more you kind of try to think of the picture underlying the process of what the calculator actually did, the better. That way it's not some mysterious black box where we take any number as fact. So let's go back to the right syntax on this one. Lower dot tail, false. Well, that's one down, but don't forget this part right here, the practical interpretation. In a certain sense, that number 0.0515 is completely useless to us unless we can take that information and communicate what it actually means to the layperson, someone who's never taken a statistics class. Imagine you are reporting on the news about something that happened on the highway, for example. There was a huge accident on US 20, by the way, in Idaho Falls. So for our practical interpretation, that's a really weird problem right after an accident too, brake light reaction times. But anyways, let's finish off our practical interpretation. The way it goes is, me personally, I like to mention the probability first. And you can say there's a probability 0.0515, no harm done there. I feel like it's better to say there is a 5.15% chance that, I like the percentage right here, just because it's sometimes a little bit better understood than a raw probability. It's the same thing, that's just a unit change. After we say that, we go inside the probability statement, and we're just reading this out verbatim, left to right. You have to recall what X was. It's the reaction time to a brake signal. And you don't have to write out all of that. You can paraphrase as long as you're bringing in enough context so the sentence here would make sense. So we'll say here, there's a 5.15% chance that, pausing on X, their reaction time to a brake signal Then over here, we can say takes more than 2 seconds. And I notice I pretty much ended the statements right here. I would say that's a pretty good practical interpretation, same down below. But if you wanted to be a little bit more specific, recall that the drivers came specifically from the study. We're not talking about modeling the entire general population of some area, just people in that one study. So you could say here, takes more than 2 seconds for a randomly selected driver in this study. So that's our practical interpretation. By practical, what we're meaning is pretty much just words, no special symbols, no special terminology, that kind of thing. Something anyone could understand, whether they're in a statistics class or have taken a statistics class or not. Any questions at all, folks, with writing out this so far? Okay. One thing you can now imagine is, suppose we were, let's take a look. I forgot when the exam is. Suppose we were on this date, Wednesday, February 7th. We're doing an exam. I couldn't ask this question of actually calculating 0.0515, but the practical interpretation would be a standard kind of concept question that would be on the exam. We will be posting sample exam problems, so you'll get a feel for what those questions look like. But that's essentially what the exams are all about. Concepts, and the homework is more about computation. Well, any questions at all, folks, with part C? Okay, well, let's go off to the, oh, there is a question. Awesome. Zachary says, do we have to draw or implement the distribution graph in any of these parts? No, not at all. So I would say the graph you see here, think of that like scratch work. I would probably even put that on different pages. I'm drawing out the problem. The only time you do have to do a graph would be for a question like this one. I believe I did ask it in the homework. There it is. It says sketch the graph of the density curve F for this distribution. We did it by just using technology to sketch that graph. And you're welcome to do the same. The syntax is this right here. The only things you would need to change are mu and sigma from those two. But what's also completely acceptable that we mentioned is you could just freehand sketch it when you're doing this on the assignment. So let's put that here just for a little bit of an emphasis. Oh, well, maybe not there. Let's put that back. Let's put it over here. So let's say here for the homework, RStudio. So what we mean is that graph there using RStudio, or a freehand sketch will work great. And let's do that freehand sketch. So if it says sketch the graph of a density curve, that could be a concept question. It should look about like this. It's the density curve for the normal distribution, but because it's any density curve whatsoever, or let me say that better way, any density curve whatsoever can never dip below the x-axis. So we have to know to start drawing it out like this. The normal curve is symmetric, has that mound shape. And if you gave me this as your freehand sketch, I would say that's great. You could put in 54, and I wouldn't be worried about all of these values on the horizontal axis. That center would probably be really all I would ask. Does that make sense for that question or expectation so far, folks? Okay, so really all we're doing in the homework is drawing it so we have a mental picture. And if you really want to get a good mental picture, the more you draw things out, write things out with your hand, the more it just sort of seeps into your brain, which is what we want, to absorb all of this technical information about probabilities. Any other questions at the moment? Okay, let's go down to, back to those brake lights. Now we're solving an equation. That seems kind of random out of nowhere, but the way this part D is going to work is, imagine it's part C done backwards. What I mean by that is, part C could have been written in this way. We might ask, for what value of K Well, we have X greater than that K value, resulting in a specific probability. The question now is, what is this value? Because we are given a probability, we don't need to use the p-norm function. We know its probability. But now we're looking for a value K on the horizontal axis. We're trying to find the right location so that we get that as probability. That's not too bad. We just change from P for probability to Q for quantiles. We'll use a Q-norm function. We'll give it not a value right here, we'll give it an area. And they supply this with 1, probabilities are areas. We'll give it a mu and sigma and decide if we have to control the lower tail. Looks like no, because this one is less than. And that's really the only thing new if you have to solve an equation. It looks a lot more abstract, and honestly, it kind of is. But once you get fluent with it, it's just another different syntax right here. We should probably fix this before we get too far ahead. Now let's give this one a try. Just to help out for what it all looks like, I'm going to start with the graph. Oh, this one's not great. But just to emphasize, we don't have to have a perfect graph. Let's let that one stand. Center is at 1.25 seconds. So I'll put that in. And now I'll just rewrite this so we can blow it up a little bit bigger. We want to find the probability that X less than, stick to a different color maybe. Probability X less K, we want it to come out to a 0.10 in probability. Now, first thing we want to decide is, where should K go in this graph? Any volunteers say over Zoom on where K should be? Should be to the left or to the right of the center?
To the left.
I agree, absolutely. I agree with Hannah as well. Thanks, folks. Yeah, when it says X less K is 0.10, that means we have to place K here. Reason being, that area is small, that area slash probability, and we want area to the left of K to be that amount. So right at this boundary, we get that area that we're looking for. 0.10 goes right here. Does that make sense to folks so far? Okay, this graph, again, it's not major, it's not required, but it's really tremendously helpful because if I mess up my syntax, I'll know right away based off this picture. K has to be a lot smaller than 1.25. So sometimes these statistical problems start by look before you leap. That's really good advice sometimes. Let's put it down right here. Just as a reminder, if you're struggling getting the right value for K, it might be because we're not thinking about the picture. So my big advice would be look before you leap. Then once we have the picture, we're basically done. It's kind of amazing. Go right here. The syntax is going to look like this. We want that value. It's going to be equal to Q norm. Input into the Q norm function is the area itself. So 0.10. But after that, it's back to mu and sigma. By the way, if you're curious, for some strange reason, Microsoft decided we only are allowed 3 pens maximum, or the whole program crashes. Don't know why that is. So that's why I'm always switching pens, if you're curious. But that's our syntax right here. And if we weren't accumulating area to the left, if we wanted this area to the right, we would have just put in lower dot tail is false on this. So now let's go calculate it out. This one is going to be, oh geez, I skipped a part somehow. I think we went B, part C. The alphabet's a struggle sometimes. Now we're on part D. So we'll put in Q norm. First thing you put in is a probability, 0.10. Next are the 2 parameters defined above, U, sigma. And that should do it for us. So let's execute the code at this stage. And we're told that K should be 0.66. This is a good moment to decide, is that number even reasonable? What would be the unit to the 0.66? Anyone happen to know what the unit is on this?
Just be seconds.
Good call, absolutely. It would have the same exact unit of x itself in seconds because that's the time to respond to a brake light. So it's saying there's about a 10% chance that a randomly selected driver from this study will respond to the brake light within 0.66 seconds and some change, or even less time in their reaction. These must be the high reaction time people in the study. So let's put down the value k equals. I lost my there you go. I'll round this one to 2 decimal places since it makes sense for the unit on this problem. So k is 0.66 seconds. And putting in that unit right here helps out a ton with this right here. Essentially, it's hard to even put down a unit unless you're thinking about what the practical interpretation would be in the first place. So kind of the goal in these problems is always think about that at every step of the way. What is x? What does it represent? What are the units? And then it makes this part not so bad. We're pretty much just going to read it out by stating this and reading that left to right. So it might read, there is a 10% chance that, next I'll move over to X and say, you might say a randomly selected driver from the study or just the driver. Let's go with that route, that the driver reacts to a brake light in, now we can say the units right here, or the amount right here, 0.66 seconds. Or less. A couple comments on this one. Probably the first comment is, don't forget this one. The probability that it equals exactly 0.66 seconds is 0. We have to have a range on that, and that's this portion right here, mentioning the inequality. So without that, our answer is not quite correct. But there's even more about this. It's a little bit off. If you're curious, let's delve into it a little bit further. Has anyone spotted something that's weird about the statement here and the practical interpretation we wrote right here? It's weird, but it is allowed. It just seems to flow in a funny way. It's really kind of subtle, and it wasn't something that I would spot myself personally, but someone has spotted it in my own work. But it turns out to be a non-issue. It's just a weird curiosity. When we wrote this out, we were saying x, the reaction time, is strictly less than k. But down here, we're saying reacts at 0.66 seconds or less. That's a statement that goes this way. It's as if we changed the entire symbol in the probability question from strictly less than to less than or equals to. This turns out to be a pretty important concept question for probability models, a potential exam question. Anyone see why this is actually allowed to make a practical interpretation that reads out this way when the question was that? Definitely kind of weird, right? Here's what the major thing is about it. When it comes to these probability models, the continuous ones where we're using areas for probabilities, this line segment's right here, right exactly at k, it has probability 0. It's just a consequence of the model. Some people think of it as a defect, but that's just really what our model does. And so for a clarification on what's going on here, recall that since probability x equals 0.66 is 0, it turns out that probability x less than 0.66 is just the same as probability x less than or equal to 0.66. And so in your practical interpretations, this is allowed. You can write this out in whichever way just seems to flow about right. conveys the right meaning that you're thinking about. I'm not worried about that and implying a less than or equals, since it does not make any difference in the probability statement otherwise. But we did it, folks. That's our first top-down, full all parts problem on probability. Any questions at all on getting through that one? Okay. Well, I felt like before just jumping into a brand new problem, it might be good to take a pit stop. So here's our pit stop on dealing with our syntax and probability models. Like I mentioned, this is not just here in the notes. If you want to find it a little bit faster, instead of scrolling through our entire document, you can go right here. And I try to put these files in separately, just so that they're more easily pulled up. But it's good to take a look at them in the notes. And so here it is. So this is going to be for a model where X is distributed. Normally it mentions the mean is going to be mu, standard deviation will be sigma as usual. And if you want to calculate probability X is less than A, that's what your syntax would look like. And that's the purpose of these notes, just to give us a feel for if you're going to solve any one of these questions, you just go to any one of these 1 through 5. Essentially, any question I can ask in the homework is somewhere in here. I think kind of interesting ones are maybe 4 and 5. We just did 4. We use the Q-norm function where X is less than something. So let's illustrate 5 next. Suppose you're solving probability X less A equals P, or excuse me, X greater than A equals P. Let's put probability X less A equals, let's put in a specific value. How about, oh, and my bad there. We're doing the greater than. So let's pick greater than right here. Let's go for X greater than 2. Or rather, A equals 0.05, something like that. Sorry, it took me a minute to come up with what we want to do on this. Now that we've got it for our A value here, I would say for a 0.05 probability, maybe A is around, let's see, somewhere over here. Next thing we'll take is that probability. It represents this area shaded. And so that's the total area to the right of whatever A is. Then finally, what the syntax part 5 is saying, if you want to solve for this quantity A, then really that's all you have to do, that Q-norm function right there. So A is going to be equal to Q-norm 0.05. We give it the area first inside that function. Then whatever mu is, whatever sigma is. And then last thing, sometimes easy to miss, we have to control the lower dot tail option in the function to get area to the right. So lower dot tail is set false for that one. So if you have to find a value on the horizontal axis, you're using the Q-norm function is the big takeaway for this. And that's how part 5 is working on these notes. If you're doing something like, say, this one, that one is the P-norm. And here's what it would look like for just a fast illustration. Let's say we want to take probability X less than -2. So illustration for this one is we go right to -2 on the horizontal axis. And now we need to find this area. It's an unknown area in this process. So what we need to do is use P-norm. So the area, which is what the probability is going to be equal to, make an arrow go like that, will be P-norm. We'll give it the input value, -2, inside the probability statement. So -2 goes here. And then back to mu and sigma. So those are kind of a fast illustration of when you use which function. I'd say the takeaway for this picture here is P-norm is always asking for or giving you an area, and Q-norm is always giving you a value on the horizontal axis. But circle that maybe just for extra emphasis. Any other questions or comments, folks, with any one of these pieces of syntax? Okay, and it just occurred to me, I did forget one thing. Let's save this syntax. And dump it down here before I forget. Oh no, that didn't work, did it? Okay, so essentially, this is what you would be doing for your homework set, assignment number 3 for chapter 11. This kind of stuff to calculate probabilities. Well, now that we've practiced that, let's take a look. Here's our last example, the last one to support the homework. And after we finish this one, we'll start turning over to transitioning from normal distributions into the central limit theorem. So here's the setup on this one. It says Rochester, not sure if I'm pronouncing that right, but I'll just go with it. Rochester, New York averages 21.9 inches of snow for the month of December, they tell us. Distribution of snowfall amounts is claimed to be normal, with the standard deviation 6.5 inches. It looks like these are estimates, really, so that's probably after lots of data being aggregated. We have a random variable where x is going to be equal to amount of snowfall in Rochester in December of this year. Not too sure how much they're getting this year. We're definitely having a pretty easy year. They say next, after the random variables defined, forgot the yellow there, assume the probability distribution of x can be accurately modeled this way. So this time there's not a question of what is the probability distribution of x, it's just being given to us. So you can expect that sometimes on homework problems and exams as well. Occasionally this is a question, but it doesn't have to be each and every time. So it said we averaged 21.9 inches. So that's why this went in here. That's our value for the parameter mu. And next, standard deviation was 6.5 inches. So that's our value for sigma right here. What I'd probably do really right at this stage, even before reading part A, is let's go to RStudio and start putting in some of those values. I mean, we're going to call them up. So let's set mu at 21.9, sig for sigma at 6.5. Not too amazing syntax so far, but let's now take a look at the question. They're asking us, what is the probability that Rochester will experience 10 inches of snowfall or less this year? We'll include the probability statement in the answer, but not the practical interpretation this time. Essentially, what's happening in example 4 is this question is in reverse of the other questions. That is your practical interpretation, and we want to know what is the probability statement that would go along with it. Just for a quick illustration, this is the probability statement right here, and that's the practical interpretation that's being asked, given down right here. The purpose of doing it backwards like this is, when it comes to probabilities, it's really important to go both ways. These statements contain a lot of value, they're important, so we need to know what they mean and read them out. We also need to know how to just write them down based on what the question is asking us. So sometimes you'll see these in the questions. The other times they're gone, there's no probability statement. So there'll be an ask for writing in that probability statement, just for that extra practice. The graph is always optional, but after the probability statement, that's probably where I would start next. Well, I think we're all ready to begin with this problem. It says, what is the probability that Rochester will experience 10 inches of snowfall or less this year? Well, X is the amount of snowfall, so we begin by writing out this. For the segment, what is the probability? We put in P, that's the probability function. Because it's an honest mathematical function, we use function notation like this. This is the input, so P of something. They told us, well, Rochester will experience 10 inches of snow or less. Because X is the snowfall amount, we throw X right here. Keep that in yellow, there we go. For this, well, we have a directionality, 10 inches or less. You might write in as less than or equals, or strictly less than. Again, completely up to your option. If you went this way, you're going to calculate the probability in exactly the same way in RStudio versus this way. It will make no difference. You'll notice there's no option even in RStudio to control those two statements. But for me, what I would probably do, this is a stylistic choice, it's not as important. If it said 10 inches or less, I'd probably just go like this. Sounds like a strict inequality. And next, the 10 inches should go right here. So that's our whole probability statement. This is the practical interpretation that went along with it. Any questions at all, folks, on writing down that statement here? Okay, and just to tie in the notes, if you're coming back here for the purpose of helping with the homework, this is the probability statement. That was being asked in instructions. So if you have that in, then you're in great shape. We still need the probability, so let's begin by illustrating the situation. We're assuming normality for the snowfall. So here's X in inches. And the other problem, I didn't put this down as much, but if you like, it's not a bad idea to say where X lives. It's on the horizontal axis, put in the unit, and that'll help a lot with practical interpretations. 21.9 will go right here. Next, we need to place 10 somewhere far to the left here. Standard deviation is 6.5, so we're going to be, well, let's see here, 2 deviations, maybe around here. I would guess our X lives in about this location. I usually don't give it too much thought, just try to get it in about the right location. So our area right here is finally going to be the answer to the question. Because we're looking for area, we're going to be using the p-norm function. So use p-norm. Let's write out what we put in here. Oh, and I did put X. That's a little bit weird. Instead of putting X, it's better to put 10. Sorry about that. Let's put in the actual inputs to the p-norm that you would use. Oh dear, it's arguing with me. Let me fix Word for a moment. Sometimes it doesn't want to delete things in the way you'd expect. So 10 inches is what should have went here. And we want to know at 10 inches or less, what is that area, which will turn into a probability. 10 gets inputted up here. Then last inputs are mu and sigma. We're accumulating area to the left, so we don't have to control the lower tail on this question. So that's the graph. Next, come back here. And really fast computation, just need to figure out where our windows ought to go. I'll put it maybe here. Let's focus on the graph and put in the information. So this one is in fact part A. We're using p-norm. Input the value of 10 here, or the same 10 that came from the probability statement. Then the model, get that out of there. Mu and sigma are the parameters. Well, before we get too far, sorry, I missed that chat there. Would the probability statement be a less than or equals to? You're meaning right here in the statement there. Gotcha. Yeah, right here, you can either go strict less than, or you can go less than or equals to. It turns out this is completely up to your option. And one reason for that is it's a weird side effect of a continuous probability model. It turns out for these models, we're always going to have this situation. The probability that X is less than or equal to any number whatsoever is the same as this probability, X strictly less than that number, say 50. It's because the probability at exactly one number specifically will always return us a 0. It turns out for this kind of problem, really it's your option, whether you like a strictly less than or a less than or equals to. Does that make sense for that question there? Awesome. Thanks for asking about that. Again, that's another thing that's kind of confusing, and it does make our practical interpretations a little bit foggy. Because like we mentioned up here, on this one, it was a strictly less than, but we wrote an interpretation that would have implied less than or equals in fact. It turns out that's okay. It's not a massive worry at all when you're writing down your answers. It's just one of those weird things where we're forced to look at something that doesn't seem quite right, and try to resolve it in our mind if it really is allowed. For continuous probability models, it absolutely is, makes no difference. But if you're going to study probability, there are other probability models that exist where that makes a massive difference potentially. Strictly less than versus less than or equal can matter in other settings. Let's go down to here. Other questions at the moment? Okay, so in RStudio, we've got, well, pretty much everything we want. We have 10 coming from probability statements here or the graph, mu and sigma. So hit Control A, Control Enter, and our output is probability of 0.0336 if we say round to 4 places, 0.0336. It's a small probability, and when I look at that, feels like my 10 that I placed right here, let me put a little dot to show where it is. I should have been a little bit further to the left, but that's absolutely okay. All these graphs' purpose is just to organize information. It's really considered scratch work. So putting it into your assignment if you'd like, it might help you for studying. Not required though. But we got it, folks. Here's the probability statement. We found the probability and our work is done. For this question right here, we can now say there's about a 3.6 or 3.36% chance of having less than or equals to 10 inches of snow in Rochester, New York this year. So kind of a weird problem. It's backwards from the last exercise because we know the practical interpretation this time. Well, let's try out another one. This one is asking, what is the probability? So like before, start with the probability function that Rochester, New York will experience between 10 and 20 inches of snowfall. So we'll put in the variable x representing snowfall. Now x is between 10 and 20. So let's put 10 here, 20 here. And one choice that I make, it's a personal choice, is I usually don't put units inside the probability function, but that's not a requirement at all. Units help. You can put inches in right here, right inside your function. So that's the question. To get this one, I think this one is a little tricky. We've only done it once. And here's what the picture would look like first. We have a center at 21.9. 10 is, I'll put it where it was before, even though we know it's not accurately placed. It's okay. 20 inches is right about here to the left of the mean. And this is x in inches. So this time we need area between two different quantities. This one is kind of annoying in RStudio because we have to write out our syntax twice, essentially. This is what it would look like. To get this area, which is equal to the probability, we'll use p norm. It'll be the upper value first. And you know you've got it mixed up since you'll get a negative probability, which is impossible. We have positive areas, which are positive quantities. So go p norm 20, then mu sigma. After that, we'll subtract p norm at 10 inches and mu and sigma. So the idea behind this is, if you write just this syntax, we're starting at this barrier right here, accumulating all the area to the left, never stopping. You're actually literally going to the left forever. The domain is all real numbers, but that probably be too much. We need to take out this white space that was actually added. That's what this does. It subtracts off the white space we didn't actually want. So it almost feels like it's kind of a weird way to rig the statement, but it works. So let's put it in action. Our answer is going to be right here. And in RStudio, once I get the cursor in the right spot, there we go. This is pretty much what I would be looking at, either the probability statement or the graph. Let's look at the graph. I'd go p norm 20 mu sigma minus, then just do it again at 10. P norm mu sigma. So let's take a look how good our probability is. comes out to about just over a third. You know, that kind of looks believable actually on this picture right here. I would say that's just about right. So 0.3515 upon rounding. And we've got it, folks. That's another probability down. We're kind of cruising through these. Any questions so far? Okay, and this is pretty, again, similar to what you're going to see on your homework assignment as well. It has problems where you have to write down probability statements, problems where you have to write down practical interpretations. Expect these kinds of things, simple probability statements here and here. And occasionally you'll have to solve an equation, but it's not as bad. You're just using the Q-norm statement, or it's not too bad, rather. Let's put this on a new page and work on this one. This time they're asking what amount of snowfall describes the 1% worst cases for the month of December in Rochester, New York. We want the probability statement as well for full credit. I want to be upfront though. I would never ask this as an exam question because, I mean, in Idaho, a worst case might be no snowfall. People want to go skiing or snowboarding, and worst case might mean literally no snow at all, for example. Whereas probably for people in New York, worst case, I would imagine, means too much snow. So we're thinking loads of extra snow in this case. Let's put in that description right here. If it was an exam question, I would put in that description just to make it clear, what do we mean by worst in that setting? So by worst, we mean too much snow. Let's give this a try. Maybe first thing we can do is, let's put down the graph first. The probability statement might be a little bit tricky for these Q-norm type problems. So here's our really fast graph. And we're centered at, I forgot, 21.9 inches of snow. So here's X measured in inches. And now it says 1% worst cases. That means way more snow than the city could handle potentially. We're going to be on the very far right. Way too much snow going over this way. We want to find a value that's kind of far to the right this time. Let's place this here for K. And now we have area to the right of K, which is going to be, once I pick a color, let's go with purple, why not? That area. One word of warning is we definitely don't want to use a percentage. We need to use the probability. So convert that into a 0.01 for area. So that graph right there, that's enough for me to start putting things into RStudio. It's also a good amount of information to just write down the probability statement itself. So let's do just that. Let's do the probability statements right here, then jump into RStudio. Definitely going to start like this. And we have some things to plug in. One thing to note right away, our area is going to the right. So there is a greater than sign here. That's got to be. Also on the horizontal axis, we're measuring X inches. So that's the random variable X that goes in. And we'd like to put something here, but that's the unknown. So K goes right inside the function. This is a probability function, so it does output a probability of 0.01. And that one's purple. I think we went for pink on that one. Or a different purple, depending on how you describe that one. So there's the probability statement so far. And the answer to this question is, what is K? The moment we specify that, we're done on this problem. And just to finish off the pattern of what we did in the notes, if you're working a homework assignment, you can come back to these notes, just scroll through to find a problem or statement similar to yours. And if you scroll to this one, here's the syntax you would use. To get that K, it's Q-norm. Any volunteers for the first input you would throw into that Q-norm function? Exactly, we need that probability or area. So 0.01, as you said. Then after that, absolutely, we need mu and sigma. But we need even more on this one. Any volunteers over Zoom for the last part to tie off this function? Anyone in class might see it? Good call, absolutely. And it's not one of those things that's really critical because, I mean, if you ran the syntax as is, you're going to notice something's off, right? K is going to be way here, no snow. We're expecting loads of it. Oh, sorry, missed a chat. Yep, exactly, Tristan. We need to control lower.tail as false. So if we forgot it, we're going to get a really weird number. Always think about the context and you'll know something doesn't even make sense. Then we'd go back and just correct by that last input, lower.tail set false. So let's give that a try, see if it works. And that will finish off really all the questions on these notes. So we're just about there, folks. This one is part C. It's going to be Q norm, input, the probability from the question, 0.01, mu sigma, and let's run it incorrectly just to see what happens. That is always exciting. If we didn't put lower.tail as false, we would have gotten about 6.8 inches. And that definitely wouldn't match the picture or the description of what we're trying to say. Worst cases as in too much snow. So then we just correct it and go lower.tail, set false. And now we're up to 37 inches. That's a shocking amount for Idaho as well. It's way above the mean. So now it looks like we are really matching the spirit of this problem. That looks like the 1% worst cases will experience 37.0 inches or more. So 37.02 inches or 0.0. Well, we did it, folks. That's the last of the probability statements here. Any questions or comments at the moment on getting through these normal distribution type problems? Okay, well, again, our goal now at this point in the class is we need to segue into the central limit theorems. That's what we'll start working on when we return next week on Monday. But to get there, it's probably a good idea to run a simulation just to explain what we're getting into. So this will be our big simulation. We don't do these a lot, but occasionally, especially if we're trying to crack open something that is a dense or complex abstract subject, it's a good idea. RStudio is a wonderful environment for running simulations to explore probability statistical type questions. So we'll say here, this is a simulation for sampling distributions. The sampling distributions is what the central limit theorem is making a statement about. So to understand the central limit theorem, and it definitely sounds important, we have to understand sampling distributions. Let's write down here a definition really quick. The sampling distribution of X bar is a probability distribution much like the normal distribution we were just working on. So it's a probability distribution that specifies all possibilities for X bar. So if we're running a study and we identify a population of interest, we're going to come up with a sample size and select, say, for a sample size of 50 individuals, and calculate the sample mean, assuming quantitative data. But what's really happening is there are two populations, the underlying population you wish to study, and the sampling distribution, which contains every potential value that the sample mean could really turn into. That's weird and abstract, so let's illustrate it using RStudio. First, any questions at all about the statements right here? Okay, so for the simulation, we're going to start by I'm going to start by centering these windows a little bit better so we know what we're working with. And we need something that is not a nice population. We've been dealing with really nice populations that we're assuming normality on, and here's one that's bad. So let's gather a random sample of size n from a skewed distribution. The distribution I'm thinking about is going to be the exponential one. Here's how we can make this happen. Let's say sample gets R. We use P as in P norm to say the probability in the normal distribution, Q in Q norm to say quantiles in the normal distribution. But if we use lowercase r, we're taking a random sample from a distribution. I want to take a random sample from the exponential distribution to force it to be skewed. It'll be of size n. I'll leave it just like that. This will have an average of 1 or a mean of 1. Got to specify the sample size, so let's do it here. Let's say we are getting a random sample of size 50 from that distribution. Let's take a look at what the situation is. The histogram for sample will output down below. So imagine there's some interesting population you care about, but it's skewed to the right. Right skewed populations are probably the easiest examples are survival times, maybe light bulbs, or maybe you have a population of guinea pigs that have been injected with a virus and you want to know how long they'll live. You're looking at right skewed distributions. So for this one, first thing I have to resolve is a typo. I wrote Sam LP. Let's fix that. Sample. And here's our histogram. That's not the best view of it. Let's fix this just a little bit better. But we definitely have some skew going on there. And this is just one sample. If you highlight everything, Control A, Control Enter, here's a next sample, and same amount of skew, just different arrangement of the individuals. You can run that as much as you like just to see what can happen with this. But what we're studying here is a sampling distribution for the sample mean. So we ought to calculate X bar. Actually, in fact, we need loads of X bars. So I'm going to write this in as X bars to emphasize it. X bars will get mean of the sample that we just pulled. So running all that, we got a new sample, and the sample mean came out at a 1.12. So this is what would happen in just one study. And if these were your data, doesn't look great, right? The sample size is large, but you can't put a normal curve to that. This is skewed far to the right. Also, in probability questions, we're not necessarily interested in modeling the entire population all of the time. Sometimes the questions are more about what is the mean of the population. So we're trying to model what's going to happen to all of the sample means potentially. That's what's getting us to the sampling distribution. So what we next need to do is, well, we need to replicate this. This can never really be done in actual practice, but it is something that can be simulated. This is just one sample. We need to explore all possible samples coming from this population of sample size 50. There is a huge amount of these. We can't possibly do it, but we can approximate the sampling distribution by going for maybe, let's go for 1,000 samples or 100 samples, something like that. So that means we need a loop. Let's make this be 4. This makes me uncomfortable. I have a cheat sheet if I mess this up. 4 will need an index I in, I'll start at 2 for my indexing because I'm going to think of this one as the first sample. So go from sample 1 to sample 2, colon, all the way to n, and we'll specify our n. Let's say n gets maybe 100 times to start just to see what happens. So what we're going to do is just repeat this right here. 99 extra times is what this is specifying. So we'll use our curly brace and write out, well, what do we need to do first? We need to obtain a new sample. So this is not going to be the best code in the world, but it'll work. Sample gets REXP n. It's going to override this sample right here, but that's okay. We're trying to accumulate lots of them. And let's also just put a statement there to eliminate the histogram from plotting. So we'll get a new sample. We need to calculate a new sample mean. So we'll write X bars gets. I don't want to say mean of sample again because I'm going to throw away my old sample mean if I do that. So instead, use the operator C to combine the prior sample mean, that one, with the new one. So here's the prior mean from right up here. The next mean, we'll just literally write in that statement, mean of the sample. So mean sample. So now when this runs through, we have two means, and it has to keep on going. I'll increment the index and say I gets I plus 1. So there's my shoddy for loop. This is about the kind of edges of how I can code. I can't do too much more than that, but we'll make that work for us. So let's recall, what are we doing here? We have a random sample, we'll get its mean. We're going to get 99 more random samples from here and accumulate all of their means into one object called X bars. So now we have loads of sample means. There'll be 100 of them all together. And that means we're about to approximate the sampling distribution just by plotting those means in a histogram. So here it is, histogram of X bars. This one time, I think I would want a main title. Let's say main equals approximate sampling distribution of X bar. So running all that, let's see what happens. There's got to be a mistake there somewhere. Let's see if there is. Hey, it actually worked. And notice what happened to this thing. We went from a distribution that was highly skewed to, well, I mean, it's not great, right? It still has a right skew, but it cleaned up by a massive amount. So let's pause right here just to see what happened. Suppose you have a sample size that's around 50, and you're going to study this distribution. This could be your capstone project for you and your program, maybe your master's program, and so on. You really need to know about this information. We might feel a little bit uncomfortable because this is right skew data, but if the sample size is large enough, this is what the central limit theorem is going to be specifying. The sampling distribution goes from a population skewed to a population of sample means that starts to clean up. The skew is being reduced as we do this. And there's a great way to make the skew reduce a little bit more. But if I increase this, it's not going to help the skew at all. All I'm going to do is take 1,000 samples instead of 100. That just makes my approximation a little bit better here. So let's take a look. Yeah, it's not too bad. That looks pretty symmetric. Here's a new 1,000 samples. Hit Control Enter. Still looks about right. That's not too bad. Still, if I had to guess on the skew to this, I would probably say symmetric. It looks pretty good. There might be data right here, or else RStudio wouldn't have plotted it. So maybe there still is some kind of skew to the right. So when it comes to sampling distributions, your sample size becomes really, really important. Suppose you didn't have the ability to afford 50 samples in your problem that you care deeply about. Maybe it was just 5. Here's what happens then. Your sampling distribution still contains skew. Our population was way too skewed, along with the sample being way too low in order to use the central limit theorem. This is not normally distributed. But let's start carrying this into the notes and specify what the central limit theorem is now finally trying to say. So let's put this here. So this is for a sample size of n equals, I think it was just 5 samples. So couldn't afford too much more. Sometimes that does happen. And this is not a great outcome for us. We would have to use non-parametric methods in this situation, since this is too skewed to be modeled with a normal model with some value of mu, some value of sigma. So we're not in a good shape here, but we just saw if you bump that sample size up, your skew starts to clean up. There is a rule of thumb, and it's a rough rule of thumb, but it's also common to an introductory course like this. The central limit theorem becomes effective right around 30 for most cases, but not all. The more skewed your situation is, the higher your sample size has to be. And there's worse things that can happen aside from skew. You might have main peaks far to the right that keep emerging. There could be multimodal data you're dealing with. Central limit theorem still works, but you might need a pretty large sample size. Let's see the situation at sample size 30. Well, it's not great, but that definitely is becoming normal at that stage. We bump that up maybe to sample size of 100. That's starting to look like truly normality. It has one main peak, it's mound-shaped, symmetrical. In fact, it looks highly symmetric. These are the data that you could model with a normal distribution. And what are you modeling? Not the population. You are modeling the potential sample means that you would get from the population even before you start this study, even before you gather data. If you know the parameters of your population, you now have a set of expectations of every potential mean that could result. And that's essentially the idea with the central limit theorem. So for this discussion, it's not as much about what we did here. I'll copy the code in case you're curious and you want to play around with it. It's more important with what you see here in these pictures. So this will be our final statement. Maybe it's a little bit too big. Oh, we'll keep it big, I guess. We'll say here, at, and I think we used 100 for this. Yeah, it looks like we've settled for 100. At n equals 100, this distribution can be modeled by n, mu, and sigma, because we're seeing the right amount of symmetry for that to be effective. So the central limit theorem will say that for a large enough sample size, your sampling distribution of x bar is approximately normal. It will specify the mean, same exact one from the population, and it will specify sigma. And just to make sure we're not being too confusing here, let's put in the actual formula for sigma. It'd be sigma over the square root of n, and up here as well. So that's the content of the central limit theorem, that the mean doesn't change, the population is modeled normally, but the spread of the data is shrinking by this factor, square root of the sample size. So the bigger your sample, the more the spread is going to center around the true mean right at 1 for this distribution. So those are the ideas we're going to delve into in chapter 13. And they're also the entire foundation for why modern statistics works in the first place. Like we mentioned, trying to put, sorry, these notes scroll kind of slowly after a while. Trying to put that curve on a population, that's modeling. That's more of just trying to fit a curve to shapes. But this statement, this is an honest to goodness mathematical theorem. It was proved by some pretty interesting individuals, French people, I believe, Laguerre back in the day. So this is a precise statement about reality now. This is what really happens. Your underlying population never had to be distributed normally in the first place. The normal distribution arises from the sampling distribution of the sample and mean in a really strange way. Well, any questions at all, folks, before we call it a night? Okay, probably you have lots of questions about sampling distributions, the central limit theorem, but when we come back on Wednesday's class, that's what we'll be, chapter 13, looking at those ideas. Then right after that, we'll be well on our way in statistical methods. Well, have a great weekend, folks, a great night, and we'll reconvene back on Monday next week. Thanks. Have a good night, folks.
Thank you. Have a good one.
Thanks, you too.